Hello, everyone. My name is Ian Malone. I'm a grad student here at Earth Planetary Science Department. It's my pleasure today to introduce, forgive my pronunciation. Bottke. Okay, Dr. Bottke. Yeah, sorry. He's originally from Minnesota. He received his bachelor's in physics and astrophysics from the University of Minnesota in 1988. He later got a PhD in planetary science from the University of Arizona in 1995. He was a Texaco Prize postdoctoral fellow at Caltech from 1996 to 1997. And he was a research associate at Cornell University from 1997 to 2000. Throughout his career, he has received many awards. He also led the survey team from 2013 to 2018, and the NASA Lunar Science Institute team from 2009 to 2013. He is currently the executive director of the Science Directorate in the Southwest Research Institute Solar System Science and Exploration Division. He is also the director of the Center for Lunar Origin and Evolution of NASA's Solar System Exploration Research Institute survey. Without further ado, Dr. Bottke.
All right, thank you very much. Sorry for the long introduction. I should have given them less material. Okay, so this talk, I'm trying to pack in about as much as possible on these two different topics, which is always dangerous. But on the other hand, it's kind of fun to see how it all fits together. So I'm going to cover a lot of ground. So here we go. Okay, first of all, I want to say big thanks to a lot of the people that are whose work I'm going to be talking about in this talk. I also contributed some things, but I want to give a special credit to David Nasforni, Rogerio Daneo. They're both in our Center for Lunar Origin and Evolution survey team here in Boulder. And then also Alessandro Morbidelli and Max Goldberg. They run a survey-like team that is funded by the European Research Council they call the Holy Earth. And we always love to get together. Like when Morby comes over here, it's always a good time. You know, we're having a great time talking about how to make the terrestrial planets, how to make the moon, all the rest. So this is fun, okay? All right. So I'm going to start off my talk by discussing a few cosmochemical constraints for terrestrial planet formation. There's a lot one could say here. I don't have time, but I'm going to hit on a few key constraints which I think matter, which are becoming more in the fore given what's going on right now. Okay. So we'll start off with some of the basics, right? So most people would agree that our moon was probably formed in a giant impact, right? So an object which we debate about the size, but if you call what we call the canonical impact or the typical impact, where a Mars-sized body hit the proto-Earth, we call this body Theia that hit, it often does a pretty good job of giving us a lot of the conditions we have for the Earth and the moon. It gives us the right masses. It explains why the moon is depleted in iron, because most of the iron in Theia goes to the core of the Earth. It gives us the right angular momentum of the Earth-Moon system. And these collisions are predicted in typical terrestrial planet formation models. So this is all very good, okay? But there's a problem, okay? And this has been a problem that's been growing, I think, in awareness over the last few decades or so. And that's as follows. If you take the canonical impact and you look at the material that ends up making the moon, almost all of the moon is coming from the Theia object. Very little is coming from the Earth. Okay. And then we look at lunar samples and you look at the oxygen isotopes for, let's say, objects like the Earth and Moon, but then in Mars, what you find is that Earth and Moon are really similar to one another, and Mars are distinctly different. Okay, so if one just took a Mars-sized object in the terrestrial planet zone and hit it with the Earth, one might expect the Earth and Moon to be different, but they're not. Okay, so there's been all sorts of interesting suggested solutions for this, and I could talk about a bunch of them, but I'm going to save some time. But one possibility is that perhaps the Earth and Theia formed in a really similar part of the solar system, okay, and that allowed them to have very similar cosmochemical properties. Is that true? We don't know, but I'm going to explore that a little bit in this talk. Okay, There's also another set of constraints that's really taken the field by storm over about the last decade or so. And that's the idea that if you look at the isotope ratios of different meteorites, that you can break them into sort of two distinct classes. There's a class which we think is coming from the inner solar system, which is often referred to as the non-carbonaceous meteorites. And then we have materials that are coming from, we think, originated in the outer solar system, probably in the giant planet zone or maybe even beyond. And we call those the carbonaceous chondrites, right? And the separation between those two was probably produced by some kind of pressure bump, which may have eventually led to the formation of Jupiter. But at some point early on, there stopped to be mixing between the two. And so they developed very different cosmochemical properties. Okay, so we're going to use that in an interesting way. So there was a paper that literally just came out a few weeks ago by Hopp et al., which I thought was really exciting. And so what you're looking at on the left side is a plot of zirconium isotopes versus iron. And what you see is the red show the non-carbonaceous meteorites, the blue show the carbonaceous chondrites and the rest. And then down here at sort of the lower left, you see you have the moon and you have the Earth in green and gray. And what you'll notice that there's no combination of known meteorites that you can mix up that could actually get those positions. Okay, it's really an outstanding problem. So what's suggested in this paper is perhaps there was some kind of unsampled non-carbonaceous component that we need to make the Earth and Moon. Okay, so that means there has to be some kind of reservoir in the inner solar system that we haven't sampled with our meteorite collection, which is needed to make at least some of the Earth and possibly Theia and the rest. Okay. So this is one set of evidence. There's also some work that's been done recently by Thorsten Klein, and he presented this at EPSC, and I'm sure he's writing a paper on this right now. If you look at the left side, what you'll see is that if you look at isotopes of titanium and zirconium, what you find is that we have all sorts of NC chondrites and achondrites, and they all kind of fit within a grand envelope, with the Earth and Moon sort of being on one extreme side or so. But if you plot up the same things with zirconia and oxygen, again, we find Earth and Moon really separated from the pack. Okay, and it's not clear how you make the Earth and Moon from the known materials. And so he suggested in his talk that perhaps there was some kind of distinct reservoir that we needed, and there was mixing between the two to get the Earth. But Mars could be made from the known meteorites, but it seems like Earth and Theia and the Moon, we need something else. We need something that hasn't been sampled yet in our meteorite collection. And that's going to become a part of our story. Okay, so with that, I'm now going to take a very brief look at previous terrestrial planet formations. So keep the cosmochemical constraints in mind. They're going to come in handy during the talk. Okay, so I'm not going to go back to the ancient past. I'm only going to go back a few decades or so. And at about the time, like the mid-2000s or so, these were the kinds of models that you're looking at in this animation that were in vogue. Okay, what happened is that you would start off with a sea of planetesimals and planetary embryos. You wouldn't worry so much about the gas. You just assume the gas was there to sort of help you make planetesimals and the rest and make these bodies. Eventually, as the gas goes away, everything gets dynamically excited, and you end up growing a set of planets. Okay, and in this case, you have to start with embryos in the asteroid belt, and they chase out a lot of the mass. Okay, now these models do a pretty good job of giving us terrestrial planets. Okay, so they're not so bad. Okay, but there are some problems, right? One of the big problems is that Mars tends to be too big, and I'll talk about that in a second. But the other problem is that we get almost everything that's created is a mixture of planetesimals almost all throughout the inner solar system. Okay, so this hidden reservoir, this unsampled reservoir, it's hard to understand where that could be. Okay. But let's talk about Mars for the moment. Okay, so in these simulations, it was pointed out that the Marses you make tend to be too massive in a minimum mass solar nebula. Okay, so it's about 5 times more massive than what we see of Mars right now. Okay, so this was a problem, and it was recognized, and so somehow we need to get a smaller Mars. Okay, so that drove sort of the big advances that took place, let's say in, from the next decade to 2010 to let's say 2020 or so. And there was this idea of what was referred to as the grand tack. Okay, so the grand tack was developed by Kevin Wash and a lot of his colleagues and the rest. And so what's happening here is that imagine you have imagine you're forming things when the primordial solar nebula is still there. Okay, but the solar nebula is massive enough that when Jupiter gets large enough, it starts to evolve inward by creating a gap in the disk. And so by type 2 migration, it starts moving in. And it starts to gravitationally interact with what they called S-class planetesimals, but what we would today probably call NCs. Okay, so NC planetesimals are here. Jupiter starts to migrate inward. Okay, so this little animation will show what's happening here. So Jupiter starts to move inward. It pushes a lot of these material in, and it gives you a lot of material around 1 AU or so. At the same time, Saturn is growing from creating gas in the disk, and it starts moving a little bit faster, and it catches up to Jupiter. They both get in a resonance with one another, and then the mutual interaction of those two planets with the gas allows them to move out. And at the same time, they're taking a whole bunch of carbonaceous bodies from the outer solar system, and they're putting them into the asteroid belt. Okay, so lots of complicated things going on here. But in the end, what you get is something kind of interesting, right? So you've created a way to get rid of a lot of the mass in the Mars zone. So what they argue is this is a great way to get a low mass for Mars. And you also get mixing in the asteroid belt, which we need. You need a combination of NC and CC objects there, and this model can do that, right? So this is all very nice. Okay, so this model has been talked about a lot over about the last, let's say, 10 years or more. But I would say that cracks in the model are starting to show. And what I'm seeing in the field is that some of the dynamicists, even some of the founders like Alessandro Morbidelli, are starting to move away from this. And some of the problems we have with the Grand TAC as follows, is that this model was developed at the time. We thought that the disks could be, let's say, could have alphas like 10 to the minus 3 or so. But observations suggest protoplanetary disks probably have much lower viscosities, more like 10 to the minus 4 or so. And that's not so good for moving around Jupiter and Saturn the way you want. Okay. There's also, again, from our cosmochemical constraints, there's lots of mixing in the Grand TAC. So the terrestrial planets at some level should have very similar chemical and isotopic compositions. And the stuff that's making the Earth, at least some of the stuff making the Earth, should be fairly common in our meteorite collection. And yet we've pointed out that maybe there's a reservoir that we're missing. And then finally, the Grand TAC does a good job of truncating the disk on the outside, but it doesn't do such a great job of getting things right on the inside. Okay, and so that makes it harder to get the right terrestrial planets that you want. So again, it's an interesting model, and it can do a lot of cool things, but it may not be what we want. Okay, so from that, I'm now going to, so being a dynamicist, I'm now going to say, hey, all you cosmochemists out there, we now have another model for you. And I can imagine all the cosmochemists right now are rolling their eyes, and they're very annoyed, and they would probably say in their minds something like this. Okay, so I've been dying to put a Marx Brothers video into my talks for years. I'm a big Marx Brothers fan, so there you go. But I do think this is what the cosmochemists say. It's like, oh God, the dynamicists are giving us another model. Okay, well, I'm sorry, but it is what we do. Okay, so I'm gonna for probably the next 20 minutes or so, I'm gonna be talking about ring models for terrestrial planet formation and how they seem to be really coming into vogue in terms of what we can do here. Okay, so why rings? Why rings? Well, some of the work on rings is being driven by observations that we're looking at nearby protoplanetary disks, and we see evidence for rings in them, just physically looking at them. Like, it's like here's the ALMA disk around H. Altairi, and you could sort of see there's a lot of interesting things going on there. And it's been suggested that some of these rings we may be looking at may be related to sublimation fronts, okay, where things are condensing out and they're creating pressure bumps. And they could also be related to planetesimal and plant formation as well. Okay, so there's all sorts of interesting things here, and we're dynamicists, we're trying to take advantage of this. Okay, so here's a schematic that was put together by Alessandro Morbidelli in his paper in 2022, where he suggested let's look at the disk at a very early time, so only about 500,000 years after the first solids and the rest. Okay, so he suggests a system where we may be able to develop what's called a sort of a silicate condensation line, where silicates are condensing out of the disk. It's creating a pressure maxima, and it's allowing dust to evolve towards there, and all of that is helping to make planetesimals. Okay, so lots and lots of planetesimals may be getting made around 1 AU, and if they form early enough, they can differentiate. Okay, so you might be getting the parent bodies of iron meteorites from some of these things. Okay, now further away, we have, maybe 5 AU, maybe 3.5 AU. People debate about the distance, but we get an ice or frost line. Okay, so again, we're getting material condensing out of the disk, and we're possibly making planetesimals there. And again, if they form early enough, maybe we're in a position where we could start to make the cores of the iron meteorites that come from carbonaceous chondrites, right? So this model is interesting in that perspective. Okay. But so this is part of it. But another part of this is this very stubborn paper that we've had around since about 2009. And it was written by Brad Hansen at UCLA. Okay, so what he did at the time is that we're trying to do all these different things with planet formation, but he just said, look, let's just try something simple. Let's create a ring of embryos. Let's just take a bunch of embryos, put them between 0.7 and 1 AU. Let's let them evolve and see what happens. And it turns out his models did a pretty good job of giving us the right size Earth and Venus, and as well as Mars and Mercury. Okay, and it's just he didn't do anything complicated. He didn't have a justification for why the ring would exist. He just said, let's try it, and it worked. Okay. And later models that David Nasforny did in 2021, he started with very similar initial conditions, but more things in it, more planetesimals and all the rest. But in the end, it tends to do a pretty good job of giving us a good set of terrestrial planets. And Sean Raymond has argued that the only known solution for the mass distribution pattern of the terrestrial planets on the semi-major axis is from something like a ring. Okay, so this is very suggestive. Okay, but all of these models we've been dealing with so far have not been accounting for gas in the disk. Okay, so when you start to worry about gas in the disk, you have to start to worry about how the protoplanets will interact with the gas. And so all these models now, we have to start going forward with planetesimal formation and with planetary embryo evolution and the rest, we have to worry about gas. So a key part of this is something called type 1 migration. So the idea is that you have a protoplanet that's large enough that starts to launch spiral density waves into the disk. Okay, and then what happens is that the gas starts to interact with all sorts of resonances, Lindblad resonances, co-rotation resonances, and the rest. And you can add up all the torques, and you can see what happens to the protoplanet as it's getting torqued by all these gas density waves, or by essentially what's going on in the resonances. And typically, for a typical protoplanetary disk, the net torque is inward. So these guys move inward. Okay. Okay. So if you take sort of a minimum mass solar nebula, and you give it a density distribution, like what I show me here on the black and the dark line here, you can see the dark line gets, increases as you go towards the sun, because many people argue that's the way it should go. Okay, if you do that, what happens is, again, your objects are going to move inward, and so we can put that into a planetesimal formation model and a planet formation model. So this little animation I'm going to show you on the right shows semi-major axis, and then it shows mass and Earth masses on the y-axis. Okay, so as things get higher on the plot, they get more massive. So we can sort of, we could put that on. I start the movie, start the movie. And what you can see is things get more and more massive. As they get more and more massive, they start to migrate inward, and then they actually go into the sun. Okay, and this goes on for a time and the rest. So what's really happening here is you're not really giving us the kind of ring we want in order to make the terrestrial planets. You're getting a very different distribution altogether. Okay. And so this might be what it'll look like after 10 million years. And that's not going to give you, if you numerically integrate that further, you're not going to get a good set of terrestrial planets from that. Okay, so what do you do? So Mirabrosh and his colleagues came up with a really interesting idea a little bit later. And they said, look, this gas disk that you have can be influenced by magnetically driven winds from the star. Okay, so you can actually deplete the density of the gas as you go away from the star a bit. So now imagine that we're dealing with sort of a blue line and the rest. If you take a protoplanet and you put it there, okay, and you look at how all the torques match up in type 1 migration, what you find is if you have the right distribution of the gas disk, you can actually cause objects to move outward. Okay, but objects that are further away don't see what's going on in the inner part of the disk, so they move inward. So this is something called convergent migration. Okay, and what it can do is it can give you a system of embryos and such that might be very much better at sort of giving you a ring-like structure, which can give you a good set of terrestrial planets. So this was developed by Mirabrosh and his colleagues. And lately, and this is a paper done by Wu et al., which includes David Nasforny and Alessandro Morbidelli and the rest. What they did is they're trying, let's say, a disk which is less depleted than before. And you can sort of play games with how depleted you want the disk to get. And if you get a little bit less depletion, you can get a better set of initial conditions for your embryos after they've formed out of things. Okay, so putting this all together, so what your goal here is to sort of get what this is a slide from Morby. He calls this a Hansen-Nasforny-Isidoro ring to give credit to all the people that have been thinking about this. Okay, so we can try to put this all together. So this is some work that David Nasforny has been doing as part of our Chloe group over like the last, let's say, about a year or so. Okay, and on the left, what you have is a map which shows the direction of migration depending on how massive you are and what semi-major axis you are. Okay, so if you're about an Earth mass and you're at 0.5 AU, you're going to move outward by type 1. Okay, but if you're at the same mass and you're at 1.5 AU, you're going to move inward. Okay, so that's where the convergent migration comes in. Okay, at some point, what happens is some of the resonances they go through a period where they start to the co-rotation resonance start to saturate, and so at some level, then you only move inward. But for other cases where you're less massive, you can move inward or outward. So we put that into a model to see what happens. So we're starting a ring here at 0.5 AU, and you're going to see what happens. Okay, so the objects start to form. They start to move outward by type 1 migration. Okay, they reach a point where they're not really migrating so much anymore, sort of reach a steady place. Okay, and then this movie will speed up in a second, but eventually this all goes together. In just a second here. Okay, and then you can get a good set of terrestrial planets. Okay, now the boxes you see, the red box, the blue box, and the green box, all they are is just sort of a metric for declaring success. And you can make these boxes kind of whatever size you want. We just chose them to be this certain size, just because it gives us a feeling for when we have something in the right order of what we want for Mars and Mars's orbit and Mars's mass. Same thing with Earth and Venus and Mercury. Okay, so we go again. So what David did is he took a big advantage of the Pleiadian supercomputer that NASA runs, and we did a lot of runs on this. Okay, so in this case, he's looking at 1,000 simulations, and so the statistics for 1,000 simulations. So we're not looking at just one case, but lots of different things. Is it pretty much you can get a good set of Venus and Earth and Mars and Mercury from a single ring model. And the angular momentum that you get looks pretty good. We have this property we call the angular momentum deficit. It's the angular momentum the planets have compared to what they would have if everything was on a circular orbit with no inclination. And if it's low, that means these planets are probably pretty stable. And so we can sort of have a measure of what our solar system is like. And so the AMD looks pretty good here. But a problem that comes up in this model, and this is something that really frustrated us, is that in general, you don't get a good separation between Venus and Earth. These models give you Venus and Earth that are much more separated than what we see. And you can sort of see that in this little plot I have over here. What we need is the separation to be about 0.277 AU or so. It'd be great if it's less than 0.3. Yes. Oh, okay. So it'd be great if it was about 0.3, but we're not getting that. Okay. And so David tried all sorts of different possibilities here, all sorts of ways to see if you could beat this down. And that's what you see in red. That's the separation. But in general, we just weren't getting good separations. They're always too far apart. These embryos always want to spread when they interact, and they spread too far. The few cases where we did get good separations, good success, we had convergent migration turned on so strongly that we were getting a bad set of Marses. Okay, so there was no good solution. I saw David try just about everything, and in 6 months, he was just frustrated. He could not think of a way to get around this, okay, with a single ring. Okay, but even if we got this to work, we would still have problems, okay? Because the problem is we're making everything from a single ring. And that means most of the things you're making are going to have probably very similar chemical and isotopic compositions, okay? And also, again, this issue that we should probably be sampling all of the materials that made the Earth because everything's forming in a ring. There's no hidden reservoir that we're getting here. And so the question is, why aren't we finding these unsampled bodies, okay? And then finally, one other issue that Morby has a grad student, her name is Catherine Dale, and she's been looking at some of the stuff that Dave Ruby has done and others have done. And this is like an old idea in the literature, but it's still pretty important. The suggestion is in order to get the Earth's right mantle chemistry, in order to get the moderately siderophile elements for the Earth to sort of look right, what you have to have is probably the Earth formed from very reduced materials early on. And then later on, you have to sort of add in a certain amount of oxidized material. So reduce first and then oxidized material. And the question is, how do you do this with a single ring? And there was no easy answer to that. Okay. So what happened is that about a couple months ago, back actually in the spring, Morby came to visit. And we spent a lot of time talking to him about all this. And basically what he finally said to David is said, look, let's just try a possibility. Okay, we don't have to have a rationale for it at the moment. Let's just try it. And he said, let's try to make the planets from 2 different NC reservoirs. Okay. And so that's what we're putting in, and that's what I'm going to talk about now. Okay. So the paper that we did on this is, as you can see, is published. So we're assuming that a protoplanetary gas disk depletes over time. We're putting in the kind of type 1 migration I just described to you. If the embryos hit one another, they can go through some degree of fragmentation. And then we're also accounting for the giant planet instability. And I'm going to talk more about that in the second half of the talk. But I'm not going to say a lot about it here because I don't think I need to say a lot here. Okay, for every single set of parameters that we tried, we were doing 1,000 simulations. We tried 100 different simulations in total. And then the resolution we have is we're using the parallel Simba code, but we're going to about 400 bodies to about 4,000 bodies for certain runs. And that means that the smallest body in our simulations is about the size of Ceres. Okay, but that's not great. Ideally, you'd like to get down to 100 kilometers because that's what we think planetesimals are made. So we allowed our Ceres-sized bodies to interact with the gas just like they were 100-kilometer bodies. That's a sort of a compromise, but it's the best we could do. If we really wanted to put all the, do this right and get all the 100-kilometer bodies in there, we would need the order of like 1 million 100-kilometer bodies. And numerically, we just can't do that yet. So we have to make some compromises to do things. Okay. So again, we're using the same kind of wind model I just described before. But now we're having two sources. So on the right side, you can see we have an inner source, which is about a little bit beyond 0.5 AU. It's got about 1.4 Earth masses. Then we have an outer source that's got about 0.7 Earth masses. Okay, so we're going to turn this on, and you can see it go. And what you can see here is that we have much more, at least in this particular run, we have much more success getting the right separation for Earth and Venus, and they're about the right masses. And here also, we tend to get a pretty nice Mars because we're making Mars from this other source that we've invented. Okay, so there's the run. And what we find is that when we did the statistics on 1,000 simulations here, again, we got a good set of terrestrial planets, the way we did it. But we also, about a third of our cases, gave us a good separation between Earth and Venus. And we've never seen that in any of the other single ring simulations. So we think this is along the right track. Okay. The other issue, which we got excited about, is that when you look at these models, we found there was very little mixing of the inner source with things that ultimately would get into the asteroid belt. We think the degree of mixing is at least the order of like 10 to the minus 7th or so. So if that's the case, this could explain why we have this unsampled component in our meteorite record that may have gone on to make the Earth. Okay, we have a rationale for it. Okay. So here's some of the results from, if you take all the successful simulations, you sort of put them together. So this is a plot where everything is sort of on the same thing, where it works. And you can see that the orbits we get for Venus and Earth are pretty good, and the masses are pretty good. Mars is right where we want it to be. Okay, we're a little bit high on Mercury, and that's probably because there could be all sorts of reasons for this. The probable answer is that we're not including collisions well enough because we just don't have the resolution. We need a better resolution way to deal with this, so we're a little high there. And then we even have cases where we have a few big objects left over in the Mars zone, and they might be our source of the big impact that possibly causes the global dichotomy on Mars, what's often referred to as the Borealis Basin Formation event. We seem to have the bodies left over for that as well, so that's pretty interesting. Okay. On the right side, you can see the orbital excitation of the bodies are good. Our planets tend to have the right eccentricities and inclinations of everything we want, so that's great as well. Okay.
Bill, can I ask a question?
Sure.
This is Steve Parman. Can you go back one slide?
Yeah.
About Mercury. So you're making Mercury as kind of a chondritic material?
Well, we're making it up. Oh, good.
Because Mercury is mostly core, and so there's one side of the debate is maybe Mercury was much bigger and its mantle got stripped away, and that explains the large core to silicate ratio, or it formed largely from metal materials. But if you're forming it from kind of chondritic silicate metal materials, and it's too big, that would match the models where you form it larger and then you strip the mantle off.
Could be. I would say, I don't want to spend too much time on that question because I got a lot more material to cover, but it's an interesting question. So let me return to it, but don't let me forget it. How about that?
Okay.
Well, we will have a Q&A at the end, so hold all questions to the end. That'll be great.
Yeah, I'll get sidetracked, and I got other stuff I want to cover here, but I'll come back to this, okay? Okay, so the problem we have is this, is that, okay, so we've created this second source, but we just did it because it worked, right? But we didn't have a rationale for it. So how do you fix this? Like, what did we did this? Well, this is where it's handy to have young people, right? So what happened here is that Max Goldberg, who is a postdoc with Morby, he suggested an old solution, which is something that we haven't really been dealing with in these models. And this actually goes all the way back to like LeCar and Franklin and others. And they suggest the follows. Okay, so if you have a gas disk, and the gas disk is slowly depleting over time, and you have like planets like Jupiter and Saturn, which are interacting with the gas and the rest, that sets sort of their precession rates. for Jupiter, Saturn, okay? But what happens is that as the gas starts to dissipate, it's changing the gravitational potential of the disk, and the precession rates for Jupiter and Saturn can change, it can actually go down. And what it can cause is that asteroids that have similar precession rates can actually get dynamically excited, okay? And what Max is showing here is you could take asteroids that formed in the asteroid belt. It can actually get them dynamically excited, and then they begin to interact with the gas and the under through gas drag, and you can move them to around 1.5 AU or so. Okay, so this may be a way to have a whole generation of things formed in the asteroid belt, but then move them out to the Mars zone, and then you can get a much more concentrated zone there for creating your Mars, and that could give you a possible way to get a second source. Okay, so from a schematic standpoint, it looks something like this. So imagine you had an inner source, which is mainly more reduced material, maybe something like enstite chondrites, and again, this unsampled material, which is probably enstite chondrite-like in some properties. And then you have more oxidized material, maybe more like ordinary chondrites and some other things. And they all form early enough that all these objects could possibly be differentiated, and you can make iron meteorite parent bodies and the rest. Then you have a resonance sweeping that takes place that moves them all into the Mars zone, and then you can start to have terrestrial planet formation and the rest to take place. Okay, so just to sort of show a model of this is a Max Goldberg movie he put together. So the inside is more reduced material and the outside is more oxidized material. And then you're going to see how you have the sweeping resonances move this all in, and then you get accretion. Okay, so you're making the terrestrial planets, you move in the asteroid belt stuff, and then you have some crosstalk between them two. So some of the reduced material is hitting the oxidized material, some of the oxidized material is hitting reduced material. But in the end, you end up with a system where Mars and the Mars you make and the object you make for Earth and Venus and probably Theia are very different from one another. Okay. So what do we get from this? Okay. So if we use David's model of trying to get planet formation here, what he finds is the Earth is made from about 70% of the inner source and about 30% of the outer source. Okay. And those numbers are pretty interesting because Catherine Dale would argue from her work that what we need is about the Earth to be formed about 3/4 from reduced material early on, and then you need to add in about 1/4 oxidized material. So our percentages are right where we need to be. And if you do this, then you can explain the nature of the mantle oxides we have. You can explain why the Earth has a superchondritic aluminum silicate ratio. I think it does a good job on getting you the moderately siderophile elements as well. So there's lots of things to like there. And again, what we in the bottom plot over here, we see that Mars is made from about 90% of the outer source. And this would provide a natural way to give you a distinction in oxygen isotopes between the Earth and Moon and in Mars, provided that Theia is very similar to the Earth. Okay. Now, the question is Theia identical to the Earth? I don't know yet. We have to do more modeling of this, but it could be some more similar than people have thought in the past, and that might give us some advantages in terms of trying to deal with this isotopic crisis. Okay. So I'm almost scared to show this plot, but it's just a schematic, but it's something I tried to put together looking at some isotope results from a paper by Rufanacht et al. In 2023. So this is sort of my picture of where I think everything formed in some level. Okay. At least for the NCs. Okay. So imagine that in the zone where you have Mercury and Venus and Earth, at some level, you're making this unsampled stuff, which is kind of like enstite chondrites. Beyond that, you have stuff that we have sampled that is in our meteorite collections. You have enstite chondrites, you have things that make the 1AB irons, winonites, aubrites, and all sorts of things. This is all happening very early. So even the enstite chondrites you're forming here are probably differentiated. Okay. Beyond that, you have material which is maybe more like ordinary chondrites, and some of that is going to be differentiated. And then finally, way out here, you maybe have your angrites and your urolites and all the rest. Okay. So they're also differentiated because they're forming very early. Okay. And then this would be what you would call the main belt zone here, okay? But now if we assume that secular resonances are going to sweep these objects out of here, these objects are going to move out of the asteroid belt and go into the Mars zone, okay? But we're not done yet. We still have several million years of planetesimal formation to take place here. So now we go a little bit after the resonance sweeping is taking place, and now we have sort of a second generation or second wave of planetesimal formation. But a lot of these things are forming late enough that they are not differentiated. Okay, so in the asteroid belt, we're forming a lot of objects, probably like our S-type asteroids and other things, but most of them are forming too late to differentiate. Maybe Vesta was something that formed just late enough and got big enough to differentiate, but it might be the only one. And that would explain a lot of what we see in the asteroid belt, where there's a smattering of differentiated material there, but it's not obvious that most things in the asteroid belt ever differentiated. Okay. So we have to worry about the carbonaceous chondrites and the rest. So they come in, this is my little schematic. They probably come in by a combination of Jupiter encounters and gas drag. This is stuff that Sean Raymond and others have talked about quite a bit. Okay. And then finally, we have this big yellow box, which I'm showing here. What happens is once the gas goes away, you're going to get really intense collisional grinding throughout these sources. So in the Mars zone and in the Earth zone, everything you have for planetesimals, you're going to be going through lots of grinding while they're accreting and you're making the terrestrial planets or so. Okay, so something very interesting happens to some planetesimals here called hit and runs. Okay, so this is work that Eric Asfog did back in 2006. And what he suggested is that if you have objects which are differentiated, let's say one's a protoplanet and one's also pretty large, what happens is that the projectile that hits the protoplanet might not fully accrete. It might get pulled apart end from end. And a lot of the objects you have may be very, in the end, very metal rich. Okay, they might not have much of a crust or a mantle or whatever. They'll just, whatever happens to come out of this collision. Okay, so some of these objects, okay, are going to be in this Mars zone, and some of them will be accreted, but others will be sort of sticking around and going through interesting possibilities. Okay, so my question was, could some of these be captured into the asteroid belt? Okay, so we decided to look at the simulations we had done. So this is a compilation of 237 good terrestrial planet formation runs, where we've taken all the planetesimals, we put them all in the same plot. Okay, so most of the gas here in this model is gone at about 4 to 5 million years or so. There's still like a remnant amount of gas that's left over. The time of this time step is 10 million years. And so between 5 and 10 million years, as the gas goes away, the embryos start to excite things, you're going to get a lot of collisional evolution here and a lot of hit and runs as well. And what we see here is that there's something of a finger that ends up in the main belt. That's materials getting back into the asteroid belt. And then some of that stuff would probably be byproducts of hit and run collisions or just lots of collisions themselves. Okay. And what I find really interesting here is that some of this material reaches around 3 AU, which is where we see Psyche right now. Okay. So I'm on the Psyche team and I'm wondering, is this a possible origin scenario for Psyche? Okay, this is what it looks like at 15 million years. This is where we've assumed the giant planet instability happened at about 11 million years. So this gives an extra excitation to the main belt. So you can see these things going away. Some of them are unstable. And then 100 million years, this is what's left behind in the asteroid belt. Okay, so we have sort of an interesting dynamical spread between about 2 AU and about 3 AU or so. Our capture efficiency is the order of about 10 to the minus 4 or so. And so I'm wondering, could this kind of model be the source of some of our exotic asteroids? We have many M-type asteroids. Some of them look like they might be N-type chondrites. Others might be iron meteorite parent bodies, and maybe Psyche fits in here as well. We also have interesting asteroids like A-types and E-types, and they may be related to very olivine-rich objects. Some of them may be related to, let's say, more thermally metamorphosed versions of N-type chondrites and the rest. And some of these things could have been brought into the main belt by this fashion. So this is what my suspicion is for how to explain some of these things. Okay. So I know that was a big data dump, but this is only part 1. Okay, now we're going to move to part 2. Okay, part 2 is going to be on early lunar bombardment. And I'm going to talk about this and then try to make some connections back to some of the work I've just shown you. Okay, so I thought it's always useful to put this in, like, why do we care about early bombardment? And the reason we care about early bombardment is that it's going to tell you about the very last stage of the planet formation. Some of the things that we've described in our terrestrial planet formation models, we need more constraints. You get them from understanding late bombardment. But it also possibly gives you constraints on planet migration into giant planets. It may even tell you something about the unknown nature of the primordial Earth. I'll come back to this. And it gives you insights into early lunar evolution. So there's a lot of things that you can learn here by understanding bombardment. Okay, so what do we really know about bombardment? Okay, so with that, I'll say the following. I've been to many, many workshops and conferences where people talk about the ages of the samples we brought back from the moon, the ages of different basins. Everybody argues with one another. Everyone's trying to get to the truth. And I would say right now I'm going to give you sort of a minimalist view of things. Okay, I would say the things I'm going to say are not disputed by most of the community. There's always some out there, outliers. Okay, I would say that from the Grail data, we probably have the order of about 40 to 50 lunar basins on the surface that have been positively identified. Okay, but most of their ages are simply not known. Okay, and I would say that's a fair representation of what the community thinks. Those that probably have good ages are really just a very limited number. Okay, and we may have age constraints on 2 of possibly the 3 biggest and youngest basins. Okay, so one is Imbrium. Imbrium is the biggest basin on the near side that everyone agrees is a basin. It's about 3.9 billion years old, and I think that's fairly robust. We also have age constraints on Oriental Basin. We don't have a sample from Oriental. People suggest it, but we don't really know if we have a sample from Oriental. But we know it's aged because it's between Imbrium and other places where we have good ages from Apollo samples and the rest. So it's probably the order of like 3.7 to 3.8 billion years ago. Okay. And then we have this big basin on the far side, which is called South Pole Aitken Basin. And its age is poorly understood. Okay. We know it's older than Imbrium. And we know it's probably the oldest and biggest basin just by looking at superposed 150-kilometer craters. You look at that, the spatial density of 150-kilometer craters on SPA is really high, and so that suggests it's super old. Okay. Now the age right now is unknown. There's been suggestions that it might be 4.25 based on the Chiang 6 samples. And Kitty Joy had some results looking at lunar meteorites that suggested maybe we're sampling SPA, and it could be 4.33. I would say at the least it'd be nice to verify those with a mission, and hopefully we'll get a mission to SPA in the near term from Artemis or maybe the Endurance rover. But that's sort of the state of where we are right now. Okay. So why is it so hard to figure out Bombardment? Okay, so there's been lots and lots of models that have put forward. And during the Apollo days, there was lots of ages that were coming in around 3.9. And so people said, well, maybe there's a cataclysm. Okay, so what's happening is that we're having all these basins form at a very similar time. And the reason they thought that is because they weren't seeing disturbances in the rocks from their lead ages that were much older than that. Okay, so 3.9 seemed like a pretty good estimate. And then other people said, no, that's wrong. We're really looking at a bias sample. And really what we're looking at is the sort of a declining bombardment that's left over from planet formation. Okay. And then there's hybrid models. I've even suggested hybrid models trying to put all these things together. Okay. But the real problem is that most of our samples, until just very recently, but most of our samples are from the near side of the moon. Okay. And they really only have ages that only go back to about 3.9 billion years ago. And so if we really want to understand early bombardment, we need to get samples that are older than 3.9 that look at other parts of the moon than just the near side. Okay. Okay. So from that sort of setting up the constraints, I'm now going to talk a little bit about giant planet migration because it helps tell part of the story I'm going to tell. Okay. So this is giant planet migration after the gas disk is gone. Okay. So to do this, I'm going to have to go back in time. So I'm going to go back in time all the way to when I was a grad student. Okay. So I was working at the University of Arizona, and my advisor was Rick Greenberg, and we were trying to figure out what can we say about planet formation. But the problem we had was as follows: is that we only had 5 planets. Okay. So we had the 4 giant planets, and Pluto was still a planet at that time. Okay. But the problem we had is that first of all, our models were suggesting that we couldn't make Uranus and Neptune where we saw them today. Okay, what would happen is that you could, by the time you had made the cores for Uranus and Neptune, the gas would be gone. So this was a problem. But the other issue was Pluto itself. Okay, Pluto was in this resonance with Neptune. It's in the 2 to 3 mean motion resonance, and it's also got a fairly high inclination. Okay, and no one had a good idea of how you could do this. And it was really puzzling. Okay, so I remember seeing as a grad student all sorts of people having talks on this, and none of it made a lot of sense, and everyone was very confused. Okay, so the big advance came from a Renu Mahatra's work, and she suggested, hey, if Pluto is sitting there and Neptune happens to migrate outward, it could actually capture Pluto in a resonance, in a 2-3 resonance, and we could explain this. Okay, and that was a big part of the puzzle. The next big part of the puzzle came from the fact that we started to discover Kuiperbelt objects. We discovered a lot of Kuiperbelt objects, and we started to see that Pluto wasn't such a unique object. There were many objects in the 2 to 3 resonance, and there were many other objects in resonance as well with Neptune. So then we could start to think about the idea of Neptune migrating outward through a structure, which we called the Kuiper Belt. And we know that the structure wouldn't be, migration would cause a lot of things to be scattered, so we can make this population much, much larger, okay? And so here's sort of a simulation of what it looks like if Neptune migrates through a primordial Kuiper Belt. And what we find is that about 99.9% of all the mass is lost when Neptune migrates through, okay? And so that means we need to start off with a population which is much, much larger, the order of several tens of Earth masses or so. So just 1,000 times larger. Okay. If you do that, then you can explain a lot of the properties we have for the Kuiper Belt in lots of different ways. Okay. Okay. But there's this inference from this. Okay. So if Neptune migrated, then the giant planets had to start on different orbits. Okay, and that sort of ultimately led to this idea of what's often referred to as the Nice model. Okay, so the Nice model is this idea that the giant planets formed in a different configuration than what they have today. Jupiter's pretty close to where it is today, but Saturn, Uranus, and Neptune formed somewhere between like where Jupiter is and about 17 to 20 AU or so. And then beyond that, you have this massive disk, which is several tens of Earth masses. But that population has to evolve to what we see today, where the giant planets are more spread out, and the current Kuiper belt has the mass of about a Mars. Okay, so we have to go from several tens of Earth masses to a Mars mass. Okay, and so in 2005, they put this together. And so what they did is they started the giant planets on circular orbits. They had a massive Kuiper belt beyond that. You can see this primordial Kuiper belt is losing mass, and eventually what happens is it causes Neptune to enter the disk, it migrates through it, and it causes instability. Okay, and then the giant planets move out to where we see them today. And this model has been was provocative at the time. It's still sort of provocative, but we've been beating on it for several decades. And if anything, the model has gotten stronger. Okay, I would say every time we see a problem in the model, we investigate it. It ends up teaching us something about the solar system, I would argue. Okay, so one thing it does is gives us good orbits for the giant planets and their major axis and eccentricities and inclinations. We have no other model that can do this. It also explains why we have Trojan asteroids, why we have irregular satellites, why we have an Oort cloud, why we have a scattered disk, why we have the Kuiper belt distribution we have. And you can go on and on and on. You can do all these sorts of interesting things. But in this original model, what we also had was a big delay before the instability. And so the thinking was, hey, this could provide a late heavy bombardment. Okay. And the same time this is happening, because Jupiter is migrating, Jupiter's evolving around, it can actually influence the asteroid belt. So the asteroid belt can lose a lot of material. Okay, so you can see sort of the asteroid belt going away here. All this stuff is going into the inner solar system. And so then we have this combination of impacts that could come from comets and asteroids. Okay, so at this point in our story, we're at the point where it looks like comets and asteroids can produce a late heavy bombardment, which is actually late, around 3.9 billion years ago. And so that's the solution, right? And for many years, I argued this because I thought the constraints were suggestive of this. Okay, and it seemed to make a lot of sense to me. Okay, but the big unknown that we had in our dynamical modeling was, when does the giant planet instability take place? Okay, does it really happen late, or does it happen early? Okay, because everything else would be the same. You can get all the same results with the giant planets and irregular satellites and Trojans and all the rest if it happens early or late. So that's not a constraint. So what happens? Well, the answer is, unfortunately, for some of the arguments I made in the past, I think the instability has to happen very early. Okay, and one key signature with this was that I remember having talks with David Sporty, and he said, I can't keep these systems stable. Basically, when the giant planets want to go unstable, they just go unstable. And it's hard to keep them in a stable state for hundreds of millions of years. There's also the fact that if you take a primordial Kuiper belt, which is several tens of Earth masses, and you get it excited just by having little Plutos in it, right, that will cause it to grind down. And because it's so massive, it grinds down fast. And so if you wait hundreds of millions of years, you lose a lot of your binaries. And also you change its size distribution to a way that we don't see it today. So in the end, I was forced to accept the idea that the instability had to happen very early. And I think that's what largely what we agree, what the community has settled on right now. Okay. So this is just sort of a fun animation from David's work. Okay, where he finds that the most successful versions of this giant planet instability start out with 5 giant planets. You have a Jupiter, a Saturn, and you have 3 ice giants. One of your ice giants is lost by interacting with Jupiter, but at the same time, that allows Jupiter to get Trojans, allows it to do interesting things to the asteroid belt, so it allows it to get regular satellites, so it's good, right? We don't know exactly when this happened, but we think it was probably within the first few tens of millions of years after this first solids, okay? But that raises its own problem, okay? Because if terrestrial planet formation happens early, if the giant planet stability happens early, then you have to worry about it during terrestrial planet formation, okay? So that caused us to make some models where we were trying to look at what would it be like if Jupiter was migrating during the time when the terrestrial planets are forming. So in this simulation, which is back from 2021, what we did is we set up sort of a Hansen-esque type starting condition for the bodies. We allowed them to make the terrestrial planets, but then we're also happening allowing Jupiter to migrate. And when Jupiter's migrating, it's actually adding an extra level of excitation to everything you see here. And you can see all these white dots that are flying around. These white dots are what we call leftover planetesimals. So they live long enough that once you have the moon forming impact, they can then bombard the moon and explain some of its bombardment record. So now we just don't have comets and asteroids hitting. We also have leftover planetesimals. Okay, so that's a factor in what we're thinking about. Okay, so the question is, well, how many leftover planetesimals do you have? It could be a lot, right? Because you're making Mars, you're making the Earth and the rest. And so it could be a lot of mass there. Well, this is something I looked at back in 2007. And I tried to put a lot of mass into leftover planetesimals. But because they're dynamically excited, they collisionally grind really fast. And the more mass you put into them, the faster they grind, right? So what happens in the end is almost no matter how much mass you start off with, you end up with sort of a similar low mass state where most of your mass is roughly about the size of, let's say, the current asteroid belt or so. So that doesn't seem like a lot of mass, but the collision probabilities for these guys with Earth and with Earth and Moon and Mars and the rest are pretty high. So you don't need a lot of mass to get what we see. So a little mass goes a long way here. Okay. And so this allowed us to put together in 2023 sort of the version of what we think bombardment is like in the inner solar system. So what you can see here is the red curve is for leftovers, the green curve is for asteroids, and the blue curve is for comets. And right away, you can see that asteroids and comets just aren't players here. They're just not nearly as good as leftovers, okay? The leftovers are a declining bombardment that's happening from early solar system time. On the top, we have time before present in billions of years. And if you'd like to start off from the first solids, we have time at the bottom in billions of years too. And what you can see here is if you go back in time and say, okay, we have 50 lunar basins. When did the first basin form that we can see? We go back in time, according to this model, it would say the first basin that we can see with our eyes formed somewhere between about 4.3 and 4.4 billion years ago. And that's not very far off where some of these age constraints are coming in for SBA. Okay, so that's interesting. Okay, not proof, but it's fun, right? We also can say, like, when did Imbrium form? Because we think we have good age constraints on that. And we find that this model predicts that Imbrium has about a 15 to 35% chance of forming at about 3.9. So that's good. Okay. We also have this other thing too. You'll notice that asteroids and leftovers have a crossover point at about 3.5 billion years ago or so. And that's actually something that we see in the size distributions of craters that we have on the moon. This is something that was pointed out by Bob Strom and Renu Malhotra like long ago. And what they see is they see changes in the size distribution going from one to the other. What they're probably seeing is the changeover from leftovers to asteroids coming out of the asteroid belt. Okay, but there's one other piece I wanted to add here, which is a part I'm excited about, and that's the following. So I've talked about there has to be a lot of collisional evolution among the stuff that's being left over planetesimals. So a lot of this stuff is in the Mars zone. Some of it may even be in the Earth zone and the rest. So there's lots and lots of collisional grinding. So our expectation would be that the impactors that are hitting the moon and then hitting Mars and the rest should be sort of the survivors of all of this collisional evolution. Okay, so we can sort of take a look at that at some level. So this is a plot by Gleisner and Becker from a MAPS paper in 2019. There's a lot going on here, but here they looked at Apollo impactites. So these are shocked rocks and impact melts and breccias and the rest. And they're looking at different Apollo samples from Apollo 14 all the way up to 17. Those are what the different colors are. These little blob colors are, these blobs are where we have different meteorite types, where like ordinary chondrites and S-type chondrites and the rest. And I should point out, they're doing this all versus like osmium isotopes, and then versus palladium and iridium and gold and iridium. Okay. And what you can see from all this setup is that some of the impactites seem to fall well within the zone of where we have known meteorites, okay, which makes some sense. But other things are well outside, okay? And the interpretation I gather from this is some people think these are probably at some level remnants of differentiated bodies that have been sort of blasted apart. So we may be looking at very metal-rich things that came from exotic places. I don't know if I can say if these things are from the Mars zone, and I even wonder, could they be things that possibly came from this unsampled zone? I don't know if anyone's ever investigated that. So it's something, I'm raising this to the cosmochemist, that maybe that's something to be worth looking at. Okay, so as I pointed out here, just that the survivors of some of these are the survivors of that may be making the impacts on the moon early fit times may be very metal rich, or at the very least they're survivors of lots and lots of collisional evolution. And that could be an interesting way to think about what we're looking at when we look at projectile compositions. Okay. There are some complications for understanding early bombardment that I haven't talked about. I'll just mention them briefly. A couple of months ago, Lars Borg had this great workshop called the Moon Council, where we talked about all sorts of issues dealing with the origin of the moon. And I think I became convinced by what he said is that we don't really know the age of the moon. Okay, it's somewhere probably between 30 and 150 million years after CAIs, but beyond that, we can't say more. But whatever the moon forms, that's going to have some influence on what's going on with bombardment in terms of what we can see. There's a magma ocean issue. We just saw, I started Steve Parman talk about this. He's got a new preprint out on this. The question is, did the magma ocean last for tens of millions of years or hundreds of millions of years? That's again going to influence what we see on the moon in terms of bombardment. And then on the lunar near side, we find this high concentration of radioactive elements, and they tend to make not only the basins bigger because they heat them up and allow them to collapse more, but also Grail found a square magnetic region with giant volcanic rifts on the near side. And that may also be influencing some of the ages of some of the samples we see from the near side. So again, there's all these things you need to worry about when interpreting the basing record. Okay, so I'll just end this with just a few open questions. Okay, so namely, so when does the moon form? Okay, what is the length of the magma ocean? I just mentioned those two. But there's also this. If South Pole Lake and Basin forms at let's say 4.3 billion years ago or so, and we have a declining bombardment, that means that projectiles as big or bigger than what would be take to make an SPA basin were hitting the moon at even earlier times. And so where's the evidence for those tremendous impacts on the moon? Can a magma ocean hide them? Or is there some way to find some trace of them in some fashion? Okay. Do we have the correct age of South Pole Lake and Basin? And then finally, can we find in evidence of the projectiles that were hitting the moon and maybe even hitting Mars, or maybe even hitting other asteroids, can we find some degree of evidence for the long lost precursors that made the Earth from this unsampled component? Okay, so here's my my summary of all my results, and I'll stop there and take questions. So thank you very much.
All right, very good. I'm going to pass the baton off to Quentin because I have to go work, but that was a great talk. Thank you.
Thank you. Yeah. Thank you, Bill. That was wonderful. Yeah, we're going to start the Q&A session, and okay, I don't know why that. All right, we're going to start the Q&A session. So for those online, you can either post your questions in the chat or raise your hand, and then for those here in person, if you want to get my attention, just throw something at me or whatnot. Okay, so we have a question from Catherine. So it says, maybe I missed this, but why did you assume the oxidized material is at larger distances from the sun than the reduced material? We see the opposite trends in the solar system. For example, Titan's atmosphere is more reduced than Venus. Or are you just referring to metals versus oxides?
Probably the latter, but I mean, I guess I would put it this way. The thinking is that in order to make the Earth, the Earth probably needs to be made from a combination of N-type chondrites and this, again, unsampled component, which is very N-type chondrite-like. And N-type chondrites tend to be very reduced in general, okay? While ordinary chondrites and the rest, which we need to make Mars. Mars is some combination of N-type chondrites and ordinary chondrites and maybe some other things as well. Ordinary chondrites tend to be more oxidized. So I think just from that, you get a sense of sort of the zonation of where reduced material is and where oxidized material is. So I think that's what we need. So I think that's what I was referring to there.
Okay, thank you for the question, Catherine. Any questions here in person? Oh, I think we have somebody raising their hand online. Let's see. Yeah, Justin, go ahead.
Yeah, Bill, great talk. Obviously, lots of stuff that you covered. And I can imagine there are other reservoirs, if you will, in addition to your second NC reservoir. Some of them lost to the sun, et cetera, but why? I mean, when I look at those mass balances, or at least those plots in which you're making mass balance inferences from, you have the planets, which are super massive, right? And then you're seeing these tiny little bodies that are potentially out spanning some other direction, and then suggesting that the Earth and the Moon have to be somewhere between two things, as opposed to maybe just having the Earth and Moon be the other end member by mass. Why I wasn't convinced that it has to be some extreme composition. When I say extreme, I'm obviously I'm exaggerating, but.
Oh, let me say, I think you're right. I don't think it has to be extreme. Maybe I should phrase it, but it has to be modestly different than what we have in our current NC population. We can't make the Earth from our current NC population. Now the question is like, you know, if the Earth sits on sort of one end of all the NCs, then
Yeah.
you have to have some way to balance that. And so then the question is, you know, where, you know, the balance you get depends on what's actually making the Earth. So if a lot of the Earth is made from NCs that are really, really close to the current Earth and the rest, then you don't have to go that far from the unsampled component. So it may not have to be very different, but I think that's something we don't know because, again, it's unsampled.
Yeah, I guess you could just make the opposite argument that the other end member is unsampled or other end members are unsampled. We talk about losing all these other bodies or objects or what have you to explain that. And I guess, you know, the centroid of the, I know this is sample limited, right? We don't have that many materials and this is a mass balance problem that you can kind of work various different ways. But it just seems like when you have the most massive amounts of material, to suggest that that's not like the central limit of the inner planets, it seems that seems like more of a you know, more of an extreme version of this mass mixing than if you had that being basically one end member and then the other stuff being strewn away and lost on the other various different other directions in the NC population.
Yeah, I maybe I'm not. Well, okay. I would say I'm trying to figure out how to come at this question. Maybe I should just keep it short. Is it? All I'm saying is that I think the cosmochemists are pointing towards the need to have an unsampled component. I think we may have a modeling reason as to how we can do that. The question is, how extreme does it need to be? I don't think we know. I mean, like, what's going on precisely in that inner source versus the outer source? Okay, the inner source, there may be things we don't know because we haven't sampled it yet, right? So that, I think that's the next, you know, wouldn't it be great to get samples from Mercury or samples from Venus, you know, wouldn't it, or anything else that would inform this? That would be great.
Well, I think it's intriguing for sure.
All right, thank you, Justin. We have another question in the chat from Ching Zhu asking, in your new model, I get the impression that Mars is forming very late, something like 150 million years. Is that correct?
No, it's forming pretty fast. In fact, it has to reach, it's probably reaching, I think, you know, there's cosmochemical constraints that it probably has to get to about half its mass by sort of the end of the gas disk, like 4 or 5 million years. And it does in this model. I think if we look at the paper I mentioned, making things from 2 reservoirs, I think we're getting a typical Mars end time formation, which could be well, okay. I should be careful what you say. Most of Mars is formed fairly early, you know, probably in a few tens of millions of years. But the question is, when does the Borealis impact come in? So if you're saying you need the Borealis impact to complete the formation of Mars, then yes, that could be late. Okay, and I think that's dynamically what I would say is from early bombardment of Mars, it would be very useful to have Borealis form at, let's say, about 4.3, 4.4 billion years ago. That would help us explain a lot of things. Okay, the problem is we have zircons on Mars that are undisturbed that go almost all the way back to 4.5 billion years ago. So the question is, can you fundamentally change Mars by the Borealis impact and, you know, create the global dichotomy and yet have zircons that are undisturbed? And I don't know the answer to that. I think it's an interesting issue.
All right, thank you for the question, Ching Zhu. Any last questions? I probably have time for about maybe one more.
Okay, and I always could go back to the Mercury question too.
Bill, if you want to address the Mercury question, you can, and then we can pretty much stop at the end.
Okay, I'll just say this. I think understanding precisely how Mercury forms is still sort of a struggle for us. I think because we're not getting, as you can see, our Mercuries are a little bit on the big side, and we're not quite getting the resolution we want. The question I have is this: imagine you make a lot of objects that are differentiated, and then they undergo through an intense period of collisional grinding. Okay, could it be that what ends up being left in the end is something that would be very metal rich that would help you make Mercury and have Mercury be smaller? Okay. Or do you really, do you need, like, let's say, a giant impact to do things? Or is there some kind of in between those two? And I don't know the answer on this yet. I think our solutions for Mercury are still not where we want them to be. So I'm open-minded, and I'd love, So the stuff that Steve is talking about, any constraints, any kind of ideas you have, let us know, and we'll see if we can make sense of them. Or we'll see if we can like model them in some fashion, see if we can reproduce what you think you're seeing.
All right.
We'll do.
Well, yeah. All right. Well, thank you, Bill, one last time. And thank you, everyone, for braving through this semester. This was the final Planetary Sample Seminar series of this year. So everyone have a wonderful holiday break, and then we'll see you guys in the spring. So take care.